Hi, and welcome back. Today we'll be looking at examples of subspaces. In the last lecture, I introduced the concept of subspace and how exactly we would derive the conditions for any subset to be promoted to a subspace. And this is the whole, verification or derivation, however you want to call it. And eventually we understood that any subset U of a vector space V would only be called a subspace if it's closed under addition and scalar multiplication, and if the additive identity, that is the zero vector from V, must be contained in U. And now we'll be looking at some examples. Alright, so one of the most common examples that I can think of is the example of a line. So consider a 2D plane. So the 2D plane is a set of points x1 and x2. Those are the components, by the way, and each of these x1 and x2 values are any real number. And so this whole plane, that is the 2D plane, and that is the vector space we are considering, and this is generally referred to as R squared or the xy plane. And now consider two lines. So one is, that is the y equals mx plus c, where the intercept is not 0, and another line, that is y equals mx. So the intercept on the y-axis is 0, and hence the line passes through the origin. Now consider the case when c is equal to 0, and hence we'll have y equal to mx. Now obviously this thing passes through the origin, that is the 0 vector, and it does form a vector space. So consider the line as a set of points. So the line is a set of points xy, such that y is equal to mx, and x and y belong to the real line. Okay, so this is something we have constrained our points to follow, and hence L will be a subset of R square. Now the identity, the additive identity 0 vector, that is contained in L, and you can verify for yourself. It's pretty easy. Just substitute y and x equal to 0, verify LHS equals RHS, and we are fine with that. Now x1 y1 plus x2 y2. So this thing is equal to x2 plus x1, comma y2 plus y1. Simple as that. Now does this point satisfy your equation y equals mx? We know this does belong to R squared, but does it belong to L? And that's what we're going to prove. It does belong to L. These are the equations that these 2 points must satisfy, and if you just add them up together, then you have y1 plus y2 on the LHS, and the m can be taken common from this, and hence you have m times x1 plus x2. This is the distributivity of the real numbers we are using, and with that we have proved that x1 plus x2 and y1 plus x1 plus x2 comma y1 plus y2, this point actually satisfies the equation as well, hence it belongs to L. Similarly, it's also easy to prove scalar multiplication, because if you just multiply a on both sides and just rearrange the terms a bit, you get that a times x1 y1, it also satisfies the equation, and hence it belongs to the line passing through the origin. But now in the case where the intercept is not 0, that is this line over here, y equals mx plus c, the intercept on the y-axis is not 0. In this case, this does not exactly form a vector space, or in fact it does not form a subspace actually. So why? Because it does not follow the closure of addition. So for example, if I want to find out does y1 plus y2 x1 plus x2 comma y1 plus y2, does it satisfy the equation? Well, it does not, because y1 plus y2 is m times x1 plus x2 plus 2c, not c, 2c. If c was 0, then we would be fine, not a problem. 2c will anyways evaluate to 0, but in this case, since c is not 0, 2c and c are not equal, and hence the addition of these two vectors, it does not belong to the subset L at all. So L is just a subset, it's not a subspace. Alright, now we'll take a bit more of a complicated example. it's the same example as a few videos before, and that is the example of a spring mass system. So again, V of R is going to be the set of all functions that map from the real to the R3 space. Alright, so this function, this vector valued function, is actually the set of vector valued function is a vector space of functions over R, that is the set of real numbers. And now consider any x vector which satisfies this differential equation, that is m times d square x over dt squared equals minus kx, and I'll consider all the solutions of this differential equation as D. So obviously D is a subset of our vector space V. We have already also established from the previous video that this D also forms a vector space over R, and since D is a subset of V, it will form a subspace. D will be a subspace of V. But that's not the point. Let's go back to how we prove it usually. So using the textbook way of proving it, the first thing we have to do is consider two solutions to the differential equation. So if two solutions are there to the differential equation, obviously they will belong to this set D. And the first thing we have to prove is the closure, but we'll prove that later. Actually proving that the identity, that is the zero vector or the zero function in this case, the zero function belongs to D, that is much more easier because all you have to do is just substitute 0 on both sides. So the LHS will be d square 0 over dt squared, and this is pretty simple. It's obviously 0 because differential of a constant is 0, and the RHS is minus k times 0 vector, and we already proved that that's basically 0 vector, and so hence this 0 vector satisfies the ODE, so it is contained in D, not a problem. Now let's look at the addition. Does addition of two solutions belong to the set D as well? So basically, is addition of two solutions also a solution? Turns out it is. So just substitute x1 in the differential equation. So that is m times d square x1 over dt squared equals minus kx1. That is there. And similarly for x2 as well. It also satisfies the differential equation. Now you have these two equations over here. Add them both together. And so you will get m times this two differentials. And now the thing is, since this double differentiation is a linear operator, you can actually club the x1 and x2 inside. So that's actually a valid move. You just club x1 and x2 inside. So this can be split into two terms as well. This thing over here. Just give me a second. So this thing over here, it can be split into two terms. That is d square x1 upon dt squared plus d square x2 over dt squared. It can be split into those two things. But we are keeping it clubbed for now. And similarly on the RHS, you just take k minus k common and you will get minus k times x1 plus x2. And so we have just proved that x1 plus x2 is also a valid solution to the differential equation. x1 plus x2 already belongs to all the valid functions from R to R cubed. That's not a problem. But does it belong to D? That's what we have just proved. It does. Now similarly, if we have any scalar A, then just multiply A on both sides of this equation. Pretty simple. A times m times x1 double dot is minus A times k times x1. Now just rearrange the terms a bit. So A times x1 double dot is the same as A times x1 whole differentiated twice. Alright, and in the RHS, we just club A and x1 together. That's not a problem. And so this way, we just saw that A times x1 for any scalar A is a valid solution as well. And so with that, D, which is already a subset of V, is a subspace over the field of real numbers. And now with that, the examples are over. We'll go through a new concept in the next video. And hope the concept of subspaces is clear to you. it can be a bit difficult to grasp where these things came from, but actually verifying that something is a subspace is actually pretty easy. It just boils down to two rules. You are already given a vector space. You don't need to establish that it's a vector space again. You just have to establish that something is a subspace, and that only takes two rules. One is the existence of 0 and the other is closure. So with that, I'll end the video and stay tuned. See you next time.